Hello, everyone. Welcome to this week's Green Bank Observatory Community Zoom. Just a couple quick announcements from me before we begin. Today is the proposal deadline. So if you have a great idea, you have a few more hours to get your proposals submitted. So just remind you that proposals are due by 5 p.m. Eastern today. Next week, we will begin our summer shutdown, and this year we do need to shut the telescope down with no movement. We are replacing a section of our foundation, about a 90-foot section of our foundation, to shore that up, and we can't move the telescope while that work was happening. So this will take about 2 months to complete. So the telescope will be inoperable for routine observations during that time, but we'll have a much better telescope when that work is complete. So I'll hand it off to Jay Lockman, who will introduce today's speaker.
Thanks very much. Today's speaker is Reshma Thomas from West Virginia University, speaking on magnetic field reversal in the turbulent environment around a repeating fast radio burst. Let me remind everyone to submit questions through the Q&A button at the bottom of the screen. And also this presentation is being recorded and will be available for later viewing on our website. Okay, take it away, Reshma.
Thank you, and thank you for the opportunity to speak in this webinar. Let me share my screen. So yeah, I hope you all can see my screen. So I'm Reshma Thomas. I'm a fifth-year PhD student at West Virginia University, working with Dr. Sarah Brooks-Polar. And today I'm going to talk to you about a recent paper that I had titled Magnetic Field Reversals in the Turbulent Environment Around a Repeating Fast Radio Burst. This paper was heavily dependent on GBT data, so thanks to Green Bank Observatory for that. So with a quick introduction about fast radio bursts. Fast radio bursts are millisecond duration, so possibly from some compact object. Extragalactic, most of them are. Highly energetic radio bursts. The first FRB was discovered in 2007 by Duncan Lorimer and his student at West Virginia University. And here is the image of the famous Lorimer burst, as we call it. So the field of FRBs have been growing so rapidly since then. So with the first discovery of a very high signal to noise FRB in 2007, until in 2011, people thought these were artificial and were from microwaves. And in 2013, there were more detections of FRBs, but they were all one-off events. And in 2016, a repeat burst was discovered from one of the FRB, and there was the beginning of the repeater population of FRBs. And in 2017, this repeating FRB was localized to a dwarf galaxy. And in 2019, the non-repeating FRB localization took place. And in 2020, there was an FRB-like burst emitted from a galactic magnetar. And in 2021, Time released their first catalog with 500 new FRBs. And in 2021, again, an FRB was localized to a globular cluster in M81, challenging many origin models. And now we are seeing unprecedented variations in the observed properties of FRBs, which points to a dynamic environment around the source. Okay, so why use GBT for studying FRBs? Because of its high sensitivity, GBT has been used for targeted searches for FRBs in gamma ray sources. FRBs have been detected in the 350 megahertz GBNCC survey. GBT also has a real-time fast transient search system, which runs commensally with other observations, and it's called green burst. Also, GBT has high frequency observing capabilities, which has been very useful for FRBs. And GBT also has the capability to record full polarization data which is very important when it comes to polarization studies of FRBs. So FRBs can be of two types, mainly repeating or non-repeating FRBs. So far, we have 63 repeating FRBs and about 700 non-repeating FRBs. Two of the FRBs have shown periodicity in their activity. So here is one of them, which shows a 16-day periodicity in their burst activity. FRBs also shows complex morphology in their burst structures, like some of them shows multiple components, some of them shows banded spectra, like you see here. So before going into the FRB that I'm going to talk about, let's talk about different propagation effects when the radio waves passes through the interstellar and intergalactic medium. So when an FRB is produced in its source in a host galaxy, it has to propagate through the intercluster medium, the circumgalactic medium, or the halos of other galaxies, the intergalactic medium, which is a material between two galaxies, and the interstellar medium of our Milky Way to reach Earth, to reach the telescope here on Earth. And when this radio wave propagates through this plasma, it undergoes a frequency-dependent time delay. And this delay is quantified by something called a dispersion measure. And this dispersion measure is the integrated electron column density along the line of sight. And as you can see here, dispersion measure, the total dispersion measure, is a sum from different components along the line of sight, which is the Milky Way halo, the IGM, and the host galaxy. So that's the first propagation effect. And the second propagation effect that I would like to talk about is called the Faraday rotation. So electromagnetic waves, so radio waves, can either be linearly or circularly polarized. When a linearly polarized light passes through a magneto-ionic medium, the plane of polarization rotates. And this rotation is called Faraday rotation, and it is quantified by the rotation measure. And how can we calculate this from the telescope? We can calculate Stokes parameters from the telescope data, and using those Stokes parameters, we can calculate the necessary information like the linear polarization fraction, the circular polarization fraction, the polarization angle that we observe here on Earth, etc. And this rotation measure is also a direct measurement of magnetic field along the parallel component of the magnetic field along the line of sight, weighted by the electron column density. So it gives an idea about the magnetic field between the observer and the source. Okay, so the FRB that I'm going to talk to you about today is this FRB 2019-0520b. This FRB was discovered by the FAST telescope, and they detected about 75 bursts in about 18 hours, which means that this is a very actively repeating FRB. And here are some of the burst spectrogram and the frequency average profile of some of the bursts observed by FAST. The total DM of this FRB is about 1200 units. This FRB was localized by the real fast system at the Very Large Array. And follow-up optical observations showed that this FRB is in a dwarf galaxy at a redshift of 0.24. So here is the optical and infrared image of the host galaxy. And as I said earlier, DM is the sum of different components along the line of sight. So if for a galaxy at redshift 0.2, if we add all the components contribution to their DMs, we get the host contribution to DM of about 900 parsec per centimeter cubed, which makes this FRB very unique from the population of other FRBs. So it means that there is something very dense, possibly around the local environment of the source. Then we created radio images from the VLA data, and we found that this FRB is co-located with a persistent radio source. Okay, and now it was our chance to do follow-up observations, and we did follow-up observations with the Green Bank telescope and on the GBT data, we did single pulse search using a package called EOR, which uses Heimdall to search for single pulses. And the single pulse candidates were classified into real astrophysical signals or artificial RFI signals using this machine learning classifier called FETCH. We did observations at L band, which is 1.4 gigahertz, and at C band, 6 gigahertz, and we had 9 bursts in L band and about 16 bursts in C band. But all these C-band observations were separated, were done in 3 epochs separated by about 6 months. So on the right-hand side, you can see one of the brightest C-band bursts that was detected using GBT. Okay, and on this detected burst, we did a rotation measure search. We searched on a wide range of rotation measure from -10 to the power 6 to 10 to the power 6. And we found that the rotation measure between the burst in different epochs were highly varying up to a rate of about 300 units per day. And it was not just varying in magnitude, but it was also varying in its sign. And this was confirmed by independent observations at a slightly different frequencies using the Parkes telescope. So even so on the right-hand side figure here, the rotation measure search image, you can see some of the bursts are from Parkes telescope and the rest is from the Green Bank telescope. So it was confirmed independently that this rotation measure is not just varying in magnitude, but also varying in sign. And another interesting thing that we noticed is that we had no detection at L band. So this shows that the rotation measure is highly evolving in time, and it shows a sort of cyclical pattern. Another interesting thing that we noticed in our data is that the bursts were depolarizing towards lower frequency. That means the polarization fraction was decreasing towards low frequencies. And that can be seen here in panel A is a C-band burst, the 6 gigahertz burst from the Green Bank telescope, which has a very high polarization fraction of about 80% linear polarization. And panel B is a Parkes burst at 3 gigahertz. And as you can see, it has a polarization fraction of about 20 to 30%. And in panel C is a L-band burst, and it has almost negligible linear polarization. And do we see DM variations? Well, it's hard to say to actually characterize the DM variations because of the complex burst morphology in FRBs, but we do see some DM variations, and we set a conservative upper limit of about 15 units. Okay, so using all these variations, we created a model which can answer this questions of depolarization towards low frequencies, large rotation measure, RM fluctuations, and large scattering, which came from an independent study. All this point to multipath propagation. So in that in our model, so there is a screen made up of highly magnetized screen made up of eddies or filaments, and using the observed variations, we were able to constrain the geometry of the screen, including the electron density, the magnetic field, the thickness of the screen, the distance to the screen, etc. And what physical scenarios can create such a screen? The first one being the FRB seen through the wind of a companion. The second is a shocked magnetar wind, and the third being the FRB source in the vicinity of an intermediate mass black hole. Okay, then we dived into the literature to see if this was seen in any other pulsar, in any other astrophysical systems, and we found this very interesting paper from 1993 onwards to 2004 of this amazing pulsar BE star binary system. So the pulsar 1259-63, which is in a binary with a BE star, a high mass companion. This shows huge RM variations when the pulsar is near the periastron, which is when the pulsar is near the companion. So as you can see here, the RMs change randomly and very rapidly, and they even changes the sign. So this was something close to what we were seeing in our source. And we took all the pulsars and the FRBs with the known RM and DM, and we put it all together to see that our FRB and this pulsar, which is PSR B1259-63, are the only two sources which shows such high RM variations, and also shows a flip in the sign of the RM. And if you remember, a flip in the sign of the RM means that the magnetic field, which is the parallel component of the magnetic field in our line of sight, is also flipping its direction. So since the pulsar was in a binary system, we did this analysis to see if our FRB can be something that is seen through a binary wind. We had compelling evidence for that, and we used the model to do calculations for the electron density from such a binary wind, and we got consistent values with typical binary wind densities. And for more consistency checks, we applied our binary model to the pulsar B1259-63, and we were able to recover the wind densities, which was consistent with the other published models. So summarizing FRB 1905-20b, this was discovered by the FAST telescope. It is an actively repeating FRB with a high host DM, and the second FRB observed to have a persistent radio source. GBT and Parkes observations revealed highly time variable rotation measure and frequency dependent polarization fraction. The orientation of line of sight magnetic field changes, which means that this FRB is in a very turbulent and magnetized local environment, which can be explained using multipath propagation. And such kind of sign reversals has only been previously seen in this highly eccentric pulsar BE star binary system during its periastron, and these observed variations could be explained with a binary wind scenario. So yeah, thank you.
Thank you very much for a most interesting presentation. Let me remind everyone that we are taking questions now, and they can be submitted through the Q&A box in the lower part of your screen. Would you say a few words about the persistent radio source?
Okay, so this persistent radio source, we still don't know what exactly it is, but it is compact. It is unresolved in the VLA image, and it has a luminosity of about, I think, 10 to the power 26 ergs per second, I think. So yeah, and this persistent radio source has only been seen in 2 FRBs. So I cannot say that these two are associated, but they are definitely co-located. So this has been seen in another repeating FRB, FRB 121102, and this new FRB 1905-20. So still we don't know what exactly it is, if it is an AGN or if it is some kind of, I don't know. Nobody knows what exactly the persistent radio source is, but there is some radio emitting source, which is 100 parsec across, which is co-located with the FRB source. I think that explains.
Does it have a non-thermal spectrum?
It has, I'm not exactly sure if it has sort of synchrotron-ish spectrum.
Okay.
Yeah.
Okay, thank you. Yeah, we have a question. Were the C and L band pulses coincident or only apparent in the individual bands?
Oh, it was done on 2 different days, so we don't have coincident observations or simultaneous observations at different bands.
Okay. And another question, is the depolarization that you see at lower frequencies partially or mostly a result of Faraday smearing in the finite frequency channels? If so, have you quantified this to get a sense of how much the depolarization is intrinsic versus instrumental?
Yeah, so we have ruled out the instrumental depolarization by using very finite channel bandwidth. So yeah, it has to be intrinsic. We have made sure that it's not. It should have been. So our channel bandwidth was sensitive up to 10 to the power 5 in L band. So 10 to the power 5 radian per meter square. So yeah, it's not instrumental.
Okay. Another question, is the actual magnetic field reversing, or is the FRB signal alternatively passing through the reversing magnetic field of the large mass host?
We don't know that yet. It could be either way. Yeah. If we don't know if the source itself is moving around this magnetic field, which has different orientation with respect to the line of sight, or if the source is stable and there is some wind that is passing, which has different magnetic field orientations. But anyway, somehow the relative orientation is changing. We don't know which one is it.
I'm struck with the density that you interpret, that you derive for the screen. Is that liable to be optically thick at some frequencies?
I think so. It is something up to 10 to the power 6. So I think it will be optically thick at some frequencies, but I'm not exactly on top of my head. I don't exactly know at what frequencies it will be.
Okay. There are no open questions. We have time for a few more if anyone wishes to ask another question. And you mentioned that the radio source was resolved and has a size of 100 parsecs, did you say?
Unresolved, and it has like an upper limit size of 100.
Ah, okay, unresolved. Okay, thank you. Yeah. Do we have any other questions? Well, if not, let me thank you very much for your presentation. It's really a fascinating, oh, here we go. It's a question about whether there are amplitude correlations with the polarity changes.
No.
No, okay.
Yeah.
Well, thank you very much for a very interesting presentation, and we'd like to remind everyone that you can review it in a day or so on the Green Bank Observatory website. Please join us on August 16th, 2 weeks from now, where T.P. Critchbaum of the Max Planck Institute will present a talk on mapping the jet origin of M87. We look forward to seeing you then. Thank you and goodbye.